Hello folks, and welcome to the third part of this series about Zcash light wallets. We are going to continue from where we left off. We talked the last thing we talked about was the Merkle tree. So let me bring back the little diagram that they had. This guy, the node commitment tree. So as a reminder, the commitment tree is where every node that is an output of a transaction, so every newly created node has a commitment, which is basically a hash of the node, and that node commitment is has to be tracked by at least every validating node, but also a light wallet, and placed in a data structure called a Merkle tree. So it's a tree. A Merkle tree is a binary tree. So every node has at most two children, left node and a right node, and it's called a Merkle tree, named after a famous cryptographer called Merkle, who invented this tree. And the principle of the Merkle tree is that at the leaf you will have the data that you want to index, and you combine 2 by 2 elements of each level in order to get the next level. So for example, here CM0, CM1 are combined together to form this hash, this node. So CM0 and CM1 are hashed together to get this node. CM2 and CM3 for this one. CM4 and this placeholder, because in this case we do not have CM5. So whenever you don't have a right child, you put a placeholder value. So we get this hash here, and then we proceed the same way on the second level. So depth 0 is this one, the leaves. And depth 1 is the first level, which has the inner nodes. So we combine this one and this one to get this one. This one here will also have to be combined with a placeholder to get this one. And now we get to depth 2, 0, 1, 2. And depth 2 we have a left and a child, so we can combine these together. And finally we have the root of the tree. So the root of the tree is something that is put in the block header, and therefore is part of the proof of work. So the purpose of this Merkle tree usually is to provide efficient way to prove that you know the content of one of the node. So that, let's say CM2. So you know a CM2 and you publish CM2, but you want also to prove that the CM2 that you are showing is the one that was used in building the tree. So in order to do that, you provide the content of your node, as well as the siblings that are required along the path to the root. So in this case is CM3, this node here, and finally actually that's it, right? Because based on CM3, this node and this node, the verifier can recompute the root, the node, and compare the result with what is part of the block header. If these values match, it proves that your CM2 is indeed the right one. And for this to work, we only need to use a suitable hash function. Okay, so actually for us, we don't really need to know why this is the real purpose of this stuff, but we should know that part of creating the spend transaction, the spending proof, you need to provide this Merkle path. So you need to be able, supposing that CM2 is your own node, you're asked to provide CM3 this hash and this hash. Okay. This is where we need to keep track of that in a light wallet. And again, we don't have to do this for every node and every node, only for the ones that we own, because the validation is already performed by an external entity, so it's external server. So we are trusting Light Wallet D in our case to have done the proper validation, because it's communicating with Zcash D, and the information that Light Wallet D gave us is accurate. So there's also a way to validate that, but that's beyond the scope of this talk. So let's see now. How this is actually done in code, right? And the problem is not trivial, because the problem here is that we don't want to keep track of CM0, CM1, CM3, CM4. We only want to keep CM2, and of course we will need a little bit more, but we still want to keep that to a minimum. So before we get to actually the data structure required for CM2, let's consider a simpler case. How do we represent this tree? Right, so we're not in that simplified problem. We are not looking at one particular node, one particular node, a leaf node. We're looking at the overall tree here. And the only problem I'm raising now is what information do we need to keep track of, and what will be the algorithm if our only requirement is to be able to add a new node, and then we calculate the root tree. So obviously you can say, okay, why don't you just store the root tree, right? Okay, that's possible, but that's a little bit of cheating. So what I would like to know is how can we be able to add nodes here? I'll add new nodes. Okay, node and nodes is very close to each other, so it's going to cause me a lot of problem. But how do we add nodes and still be able to maintain this Merkle path? Right. So the data structure for this is actually part of Libra's Zcash, and it's called a commitment tree. Pull it up. Okay, so this is Libra Zcash, and we're looking for commitment tree. This is our guy, right? We see here that commitment tree, where is it? Yeah, commitment tree is it's a struct which only contains a left node, a right node. So these are type nodes, and option here means that this is either a node or nothing, no node. So the known value is when you have a question mark, or you don't actually have data, right? So if you have a node, you will have some and the content here. If you have nothing, you would have known. So this type in Rust captures a value of the type node, but also the absence of any value. In C, you will have the pointer to node, and you will have a null when you have no node. But in Rust, it's safer to clearly distinguish between the value and the absence of a value. So left and right, so this represents, like, for example, CM2 and CM3 are left and right. And then a series of parents. So here you have a vector, and the vector is either a node or nothing. So what you can imagine is basically the commitment tree is this the stuff that I'm drawing here, this frontier, right? So in the case of the tree that you see here, left would be CM4, right would be known because we have nothing here. And then the parents would be known because the Merkle path is such that you don't need this one, right? This one is you can calculate. So there's no point in storing anything that you can calculate. So this particular case, what we store is the sibling, and the sibling here is nothing. So we're gonna have known here, right? So then the next parent is gonna be this guy here, because again you don't need to store this one. You can recalculate based on this guy and this guy. But in order to proceed further up, you will need this hash here. So in this case, the parent or the grandparent would be this node here. And then that's it. You don't need anything else because you have already reached the root. So that's your commitment tree. And you can notice two things, right? First of all, and this is purely technicality, the node that you have here is an abstract type. It's anything that can be hashed together. So we implement node as something that is hashable. And hashable here is a trait, so it's like an interface, which has the ability to be combined. So if anything, you can define this particular interface or this particular trait, which is combining a left hand and a right hand side, right hand side, together in order to get a new node. You can make a commitment tree out of that. Right. So as we see, the commitment tree is really only information about CM4, right? And the guys that make CM4 Merkle path. And the reason why we don't need anything else, we don't need anything on CM0, CM1, CM2, CM3, is because this Merkle tree is incremental. You can only append at the end, to the end. So CM5 will have to go here. And you can never remove anything. So CM3 will never be removed and neither updated. So the tree really has only one operation, and the operation is add something to the end. So because you cannot change anything that was inserted before or appended before, you know that once this node is CM2 and CM3 are provided, this hash value will be the hash value of CM2, CM3, right? So this hash value will not change because CM2 and CM3 cannot change. And likewise, CM0 and CM1, you already know they were provided because, again, the order dictates that you cannot have CM2 before having CM0 and CM1. So therefore, this node is already populated or calculated. And also, these two guys are combined to provide this one, okay, to give you this one. So by the time you get CM4, all these guys are calculated and they cannot change, right? So there's no point for you to store the value of CM0, CM1, CM2, CM3, neither the values of these two nodes here, because all these nodes here only participate in calculating the hash of this guy, right? And then with only this value, you can proceed further. So this is a very good optimization, okay? Because now, instead of having to store, let's say that the tree has n levels, it means that the tree would have a capacity of 2 power n nodes, right? So if the tree has level 0 only, then it will be 2 power 0, so only one node. If you have level 1, so level 1 is actually two levels, right? It's 0 and 1. So if it has one level, depth 1, then it has this level will have 2 power 1, which is 2 nodes, and then it doubles every time. So it's pretty easy to see that at depth n, you will have 2 power n nodes. So if we were not able to do any optimization, and because the tree can change at will, so if, for example, CM1 could be dropped, then suddenly now we would have to update this hash. Therefore, we have to keep track of CM0, right? But because this is not possible, this is never going to happen, we don't have to store 2 power n leaves. We only have to store basically n nodes, so n or n plus 1 if you prefer. So the storage cost is logarithmic in number of nodes, right? And that means that the only operation that you really have to implement here for this commitment tree is the ability to add a node, right? So you only append a node. So this is our interface that we kind of implicitly established. You add a node. You then let's see how we can handle that, right? So let's begin with an empty tree. Nothing's there, and let's see what our data structure here, the commitment tree, looks like when it's completely empty. So if it's empty, we can see actually that's the definition here, which says that the left and the right nodes are empty, and the parent vector is also empty. So kind of makes sense. If the tree is empty, the commitment tree has no information, so no known everywhere, and an empty vector. Right. So now we add one node. We add CM0. So let's see what happens if we add CM0. Well, intuitively speaking, in that case, the only thing that makes sense is to set the left to that node. So we will have left sum node. Okay. Then we add CM1, and we'll still have a slot for that. So right is empty, so we can also put CM1 here. Right, so our commitment tree now have left CM0 and right CM1, right? And the parents are still empty. So now you go and you add CM2. So CM2, well, you start to have a problem because you only have 2 slots. You have only left and right, and therefore you don't have a room anymore for a single element, right? But let's see what should happen. So if you have CM2, right, and you don't have CM3 yet, so this guy is empty, right? What you can expect is that CM2 becomes left, CM2 becomes left, so left becomes CM2, let's put it this way, and right becomes known, because basically you went and you jumped to that particular area of the tree. CM2 is left, CM3 is not there yet, so this should be known. And now CM0 and CM1 that you previously had in left and right, you can combine them together. So you can do the hash of these 2 nodes to get this value here, the value of this parent. And now your parent vector has 1 element, which is this guy. So after you insert CM2, you will have left CM2 right known, and parent will be a vector of 1 element, which is this guy, this node. Right. Okay, so now what happens when you add CM3? CM3, you still have room, so you still can put right equals CM3, and nothing else has to change. Right. So again, to recap, you will have left CM2, right CM3, and parent this guy. Okay, so now we do CM4. We add CM4. So when we add CM4, the same thing happened as before with CM2. That is to say, left and right are both occupied, so we have to clear them. So CM2 and CM3 are again combined together, right? But now the parent of so the combination of CM2 CM3 is this guy, right? And this guy is also hashed together with the previous parent to provide this guy here. So now our tree has gained one more level, right? So what do we have? We have then left is CM4, right is known, right? Then the parent is known, and the grandparent is this guy, right? So that we just got by hashing these two nodes together. So you kind of, I hope you can see at least manually how things go, right? The idea is that you feel, you try to feel the leaves, right? So you try to feel left. If it's so, left will never be empty, right? You can see that because of the way the filling algorithm works. We're never going to be in a situation where left is going to be empty, except when everything was empty. So only in the beginning, when the tree was entirely empty, we had empty left. But afterwards, left always has one value. But right sometimes has no value. And if it has no value, we can simply insert the value there. We can replace the node, the known with that node. But if that right guy had already a value, then we have to flush it up. It's like if you want to see, it's like a siphon, but in reverse, right? If this guy is full, so then when you pour something here, you have to clear these two guys, so they would go together. But now it's this guy is full. They would flush together. They would go here until you clear enough room, so that for you to insert a new node. So it's a bit, it's not super exact, but I think it's the idea of how you calculate this tree. So again here, right, for this example, the most difficult example we had so far is CM4. And CM4, we had to make room for CM4 because CM2 and CM3 previously occupied left and right. So we combine them on this guy. But now this level is full, so we combine this guy together to make potential room for the next level. So at the end of the day, you have the following algorithm. So let's keep the two frontier. We don't really need that. Size also we don't need. Is complete we don't need. Read and write we don't need. So this only this append, right? And append delegates to append inner, which is this guy. Okay, so this is the algorithm we were talking about. So we have left and we have right. If left is known, which is again this only happens in the beginning, then we set left to that node, right? So you can see that all these conditions, like these three conditions, are exclusive. It says here either left is known, here right is known, and here both are occupied, right? If left is known, we don't care about the right, which actually will be empty as well, right? But we don't really care. We could assert that right is empty, but that's not done. So if left is empty, I put the value here in the left. If right is empty, I put the value in right. And here again, you could assert that if known is here, then you have something here, right? But by the way this matching statement works, if something was if we had known would be this case, right? Because it matches the first, and then if there's it tries to match from left to bottom, and if there's a possible match, then it was execute the the right hand side, and then skip. Right? And again, this placeholder underscore means anything. It doesn't matter. So this is the case where the leaves contain has one cell that is empty, either the left or the right one. It's very easy. You just fill it up. So the only trick, well, not trick, but the only more complicated case is when both of these guys, left and right, they are both occupied. So this is this case, right? So first you combine left and right together, and this argument here is the depth. It's the depth of the tree. So we are combining leaves together, so it's going to be at level 0. Right? So you combine these two guys together. So for example, CM2, CM3 are combined together. Oh, let me put it side by side. Can I? That would be easier. Yeah, much easier. Can I close this? I thought I could close this. Not sure how. All right. Okay, there you go. So this is the case when both leaves are occupied. So you have left and right. We start combining together. So we have this value here for combine, and we can clear left and right because we have already taken their value. And now that they're empty, we can set left to the node that we are inserting. Right. So for example, we are talking about CM2. We are now clearing CM0 and CM1, left and right, CM0 and CM1. We combine them together to produce this value. And now we can put CM2 into left and set right to empty, to none. Right? CM3 is not there yet. But now there's this loop because we're saying that the combined value here may have to be propagated up, right? And you can see how it's done, right? So we loop through the parents, right? So we just go through the parents. And if the parent has a value, right? So this is the case for example, we are combining CM2 and CM3 together, and we have this combined value, and we already have a parent here. So we have already this node, right? So we know that if we have already a parent at this level, then we have to combine them. We have to keep combining. Right? This is the logic here. We have to keep combining parents as long as the parent is not a known, right? Because as I said, the image is that you're pouring glasses together, and if the glass contains already something, you have to somehow merge these two and clear that slot for the next element. All right, so we combine these guys together, and now we can set that parent to none. Right, so this is exactly what happened here. We are combining these two together, and now it's known. Right, we do that, but we have to keep going. Right, now that we combine these two levels, this value has to go back up, one level up. Right, so the loop continues until until two things. Until you reach a level which has a hole, right? The parent has none. In this case, then you have a place to put the value. So it stops here. You put the combined value there, right? And then you can stop. Right? You don't have to loop further. And the second reason why it would stop is because your tree is full. Right? You basically went all the way and you already populated all the parents. So in that case, you have to extend the parent. So this, for example, this happens on the first CM2 first combination, because at that point the parent array was empty. right? So in that case, when we had CM2, we combine CM0 and CM1, right? For this variable combine, but depth would be 0, and we're reaching. Well, depth is a constant, sorry, but we're getting out of the parent length, so we have to push the value here. Right. So this is a fairly short piece of code, right? This is not very long, but this is going to be kind of our bread and butter. This is a kind of algorithm that we're going to see over and over, either in the reference implementation for LibGraph Zcash or WarpSync. It's going to be a bunch of this type of tree traversal and manipulation and node manipulation. So I'm going to stop here because I would like, let's get some time to digest this. This is new information for you. I would like, it would be better if we are very comfortable with this type of algorithm, because this is going to be really like the same type of manipulation, but just harder and harder. Okay, and this is basically the whole complexity, the whole complexity of this commitment tree. Everything else that you see here, the root inner, all this stuff here, is really not that important. The only thing here is really your ability to append a new node. Right. So essentially, the entire file, the most complicated part, the most interesting part is these 10 lines, right? So I hope that you understand, you can get these 10 lines very well before we get the next part of this video series. So good luck, and if you have any question, please ask me on the chat or as a comment. And again, it's very important to get this very well. All right, and that's the end of part 3. In part 4, we are going to continue this overview of LibRust Zcash implementation of the node commitment tree, with the analysis of the second class, the one that keeps track of your particular node, right? So far we're talking about the tree in general, but the next object, the next class, is going to be about, okay, we want to point out at a particular node, like for example CM2, and see how we can modify this data structure, or not really modify this data structure, but how do we make another data structure that is similar to this one, but the purpose will be to keep track of a particular node, right? And again, the API would be the same. The API would be append, right? So it will also be only limited to this function append, but of course it will be a bit different. All right. Okay then. So let's adjourn and see you around on the part 4.